Hi, everyone. So welcome to our new PyHEP Topical Meeting of the month. So this time around, we will be discussing a HEP-specific package, namely PyHF, which I'm sure many of you from names already know a bit. But still, I hope this tutorial will be, this 1 hour tutorial will be very useful to many of you. All right, so I think without further ado, I would like to introduce the PyHF package because that's part of the introduction from Matthew, I'm sure. So first of all, thank you very much, Matthew, Jordan, Lucas as well for preparing this tutorial and for your willingness to discuss with us for an hour. So I'll let you start. Thank you very much.
Okay, great. Thanks very much for the introduction, Eduardo. And yeah, we're happy to be here today. Right, so today we're going to be talking about PyHF, and I'm going to try and keep this to about 45 minutes or so, just so that we kind of cover the introductory basic. But we're going to basically start by going through the new tutorial that the PyHF dev team have put together. And so from the topical meeting page, you can see that there's 2 links here. There's one to a GitHub repository for the tutorial, and then one for the tutorial Jupyter book itself. And so we're going to be working out the Jupyter book, but as just a quick tour of the actual tutorial page. So this is going to be hopefully a landing ground for people to use as a resource into the future. We've now started to consolidate the tutorials so that they will be versioned and released through this page here. So in the future, check back for new releases. Whenever we have a new release of PyHF, you should also check back for an updated tutorial. Today, we're going to be working off of PyHF release version 0.6.1. But when, for example, the next patch release comes out, version 0.6.2, this page will be updated as well, and it will all be versioned with Zenodo. So you can also get, in addition to having access to the code, you'll also have access to the actual old tutorials themselves through Zenodo as well. Okay, but you'll notice that up here, we have this link to the tutorial page itself. And so this is kind of where we're going to be working through today. This is the actual Jupyter book that is the tutorial. And so this is all going to be evaluated for you because Jupyter book renders everything out, but we're going to be stepping through the actual notebooks that comprise the tutorial to actually go through everything. So it's just some kind of introductory page stuff. So we're not going to, the focus of this tutorial is not going to be a deep dive into the statistical machinery of HIS factory itself. We're more going to be focusing on the PyHF API and how to do some common things in at least the LHC experimental world. But this landing page is going to kind of help you get up and going. So as is probably common to most of you, we're going to be working inside of Python virtual environments. And so here, this gives you some instructions on how to both set up and create a virtual environment for this tutorial, either if it's locally or perhaps on one of the CERN LX Plus clusters. So that gives you some instructions. Once you have that up and running, though, it also gives you some examples of how to actually get PyHF itself, how to install it, since we're distributed both on the Python package index, PyPI, as well as Conda Forge. This is simply just either a pip install or a Conda install for all of our releases. And then additionally, since we're going to be using some extra libraries that help augment and expand PyHF, such as Uproot and IMINUE, other nice libraries from the Feickert ecosystem, this gives you some examples on how to actually get those as well, just using our extra syntax. Okay, but for the dependencies of this tutorial today, if you're going to be following along at home, and you can do that, but we'll also show you how you can follow along just in your web browser. If you simply just clone the repository, then you can simply just pip install this requirements.txt file that it lives underneath the binder directory, and that should have everything you need to be able to run the entire tutorial. The rest of the page, this introductory page, is just about mentioning that it's very easy to go ahead and get the citation for PyHF. And then if you are looking for additional statistics references, in addition to some of the really nice tutorials that Hans has given in the past. We might also recommend that you check out some of the statistics and data science Jupyter books that Kyle Kramer has made. And then of course, if you actually have questions on PyHF itself in terms of the documentation or in terms of things that you think might be bugs, we really welcome you to come to our GitHub to either ask in the issues or to open up a GitHub discussion for there to be some back and forth. Okay, but to actually get started in this tutorial, we're going to just start at the beginning, which is getting into HIS factory models. So as I said, we're going to be stepping through the Jupyter book itself, but let's say, and I'm going to be running this locally, but let's say that you actually want to run these notebooks, but you don't want to have to take the time. Oh yes, can I post the link to the tutorial there? I can indeed. Let me just copy and paste this. Okay, great. So, right. So the question okay, so let's say you want to just be able to try and run all of this in your web browser. That's also pretty easy, because if we just go back to the GitHub source repository, you'll find that there is a link to Binder. And if I did this right, I should have pre-built the Binder image across all of the 3 Binder Federation servers. So you can simply just click this button and this will launch for you an interactive Binder session on one of the Binder Federation servers. And if sorry, for some reason my browser doesn't want to try and go over there. There we go. And you can see that this is spinning up for you right now, and it's finding a built image. And this is going to contain all of the actual Jupyter notebooks running on this remote image that on this container that we're going to be using in the tutorial today. So you can simply just actually step through them as we go. Alternatively, if you want to try and get to a specific one pretty quickly, if you're on the Jupyter book website itself, you'll see up here at the top, there's this handy little rocket icon. And you'll notice that there is a launch Binder link right there. And if you simply just click on that, then in a new tab, it will also launch it will launch a Jupyter Lab instance in Binder for that specific notebook. Okay, so if everyone who wants to follow along can try and go and launch in Binder and then get access to this Hello World notebook, which is under the book directory, then we'll start there. I'm going to now switch over to my local instance of Jupyter Lab. And let's see, let's also get this up. And I'm also going to try and take 1 second to try and play with the size a little bit, so that this is hopefully a little bit more readable on video. Maybe 125, that looks okay. Okay, so as I said, we're going to be just trying to step through the first 3 or so notebooks in this tutorial, but this tutorial exists it exists and it's not going to go away, and it should be updated in due time. And there's much more material here than we're going to cover just today, so please feel free to explore it at your leisure. But we're going to basically just be doing a quick dive into HIS factory models, because PyHF is Pythonic HIS factory, and so it's allowing you to both build and manipulate HIS factory models as well as trying to do some inference as well. Okay, so in general, if we take a view of how an LHC experimentalist view of how we want to be able to use HIS factory models, we can basically say that at kind of the simplest terms, that we are going to have some sort of physics model that we want to try and test and compare that to observations that we've made with our detectors. And so in general, we're going to split this out into our model into saying that there's some sort of signal component that we're interested in, as well as some sort of background model that, of course, has its uncertainties, as well as the actual observations that we have coming from our detectors. So we want to combine all this information into a model and then try and do some sort of statistical inference with it to try and actually make statements about the physics. So let's get going with this. At the top here, we just have some very simple imports. So we're importing JSON, Matplotlib, and NumPy as helpers, as well as PyHF and some of our contributed module visualization tools. So PyHF also has this kind of helper getting going API for building very simple HEP data or high energy physics like models. And so what you can see here is we're just going to build a model that is simply just going to be a 2-bin model that contains both signal and background information in both of its bins, as well as uncertainties on the background that are listed here. And so if we go ahead and evaluate this, then we can see that when we look at what this model is, we have an object that is a PyHF PDF model object. So let's actually explore what this thing is, because we just kind of ran a command and got something. So if we actually then, if we use our JSON tools to actually look at the model specification, okay, then we see that we have this whole JSON spec that gets dumped to screen. And let's just take a moment or so to try and decompose this and see if we can understand a little bit about what's going on. And just from what's up here, you might already kind of have some hints at this. But without, again, going too much into the HIS factory model spec or anything like this, we can, that's actually described in the paper. We're just going to say that we have one channel, which is named single channel. And by channel, this, you can basically just think of that as an analysis region. So in this situation, we're just kind of looking at one region of an analysis. And then in this region, in this channel, single channel, we have multiple samples. And the samples are the different physics processes that are going to be going on in that analysis region. And they also are the components of our model. So we can see that as this is a 2-bin model, we have a signal process that has observational data in 2 bins. And then it also has just a normalization scale factor that's associated with it, which is listed under the modifiers. And then additionally, we also have a background sample, which has, again, two bins worth of observational data. And then it also has this additional modifier that is an uncorrelated background uncertainty that, for the jargon that we're going to try and explain a little bit, is something called a shape systematic. And so it has values of 5 and 12. And to try and explain what that means a little bit, if we look at this text below here. So as I mentioned, the signal sample has a normalization factor, mu, and mu is usually what we'll call our parameter of interest. This is what we're going to usually be looking at to say, like, this is the normalization or the scaling factor for the signal process, or this is usually called the signal strength. And the background sample, as I said, it has these uncorrelated shape systematics that are controlled by these 2 gamma parameters. But what we're going to say is that we want to give a background uncertainty for the 2 bins that we have of 10% uncertainty on the first bin and a 20% uncertainty on the second. But the way that we express this is that these uncertainties are given as absolute values of the actual background process itself, and not a relative value. So to get the 10 and 20% of the 50 and 60, we simply have the 5 and 12. And so this is all of this information is actually contained in the data directory here as this 2-bin 1-channel JSON configuration. We're going to take a little bit look at this later. But so this is, oh, okay, so we have, does PyHF take into account the uncertainties on the data? Does it make sense to apply modifiers to the data? Well, so maybe I can get into this later, but when you say the uncertainties on the data, well, so I guess I would say, like, your uncertainties should come into your model, your statistical. Oh, so, well, I think this will all be addressed as I go on, but if it isn't, please go ahead and ping me again at the end, and we can go through this. But I think this should be covered as we go through this notebook. Okay, so I just said a whole bunch of words at you pretty fast, and that probably might not have made a whole lot of sense, but don't worry, because we're going to spend the rest of this notebook simply just going through all of that again multiple times. And we're also going to be using this as an opportunity to explore the API a bit. Okay, so this was a JSON model specification, or a JSON representation of our model specification, but let's say that you actually want to try and explore this a bit more in an API-friendly way. We offer that. So with our model APIs, we also have a config API that gives you access to a lot of the information you would care about. So similarly, while running this, we have these different attributes that we can access. We can ask about the channels and see that here we only have one, the single channel, but that the single channel has 2 bins. And that, again, the samples that are contained in it have names of background and signal, and that they contain modifiers of on a signal strength parameter named mu of a normalization factor, and a shape systematic on these uncorrelated background uncertainty modifiers. And then again, we actually see though that we only have 2 types of parameters. And then we also have something that is called auxiliary data. And we're going to actually touch on what that means right now, because that might be terminology that seems confusing. Okay, so I said we weren't going to do a dive into the HIS factory formalism or specification, but if you'll allow me to kind of break that promise very shortly, we can basically decompose the HIS factory probability density function, or the HIS factory model, into kind of 2 main components. We'll basically say that we have a main component of the model, which is formed as a Poisson product across all of the bins and all the channels that we're considering. But then where the rate parameters for the Poisson that we're modeling are controlled by these factors just below here. But then what we'll say is that we're going to say that we have additional model information that we want to bring into that for historical reasons is given the term an auxiliary model. But really all this is it's just using additional information about what we know to help guide and constrain in the model the actual rate parameters themselves. And so what we talk about as auxiliary data, this is simply just saying, like, in the model, in this secondary model, or in this constraint terms that also go into our model, what are the if we say that these probability density functions that are composed in the model, how are we actually evaluating them? Because if they don't actually take in direct observational data for their input parameters, but if we create additional parameters for them as well. And so we can kind of decompose that a little bit here. So if we again look at the symbolic representation, we said originally that we had this main part of the model and this auxiliary or secondary part of the model. And before we said that the main part of the model is just is a Poisson, and with the rate parameter that is going to be, of course, our kind of expected events, and the expected events here are going to be the scale factor applied to our signal process plus these gamma factors, these uncorrelated background and or these shape systematics that are applied to the background process. But we now want to try and say, okay, can we have this gamma parameter, which is this shape systematic that we're applying to our background, but can we do something, can we actually say more information about these gammas? And the answer is yes, because we're using what the jargon is, this auxiliary model, to get more information on it, or to help constrain it in our actual inference process, by then bringing in information about the background uncertainties here. And again, this is for a 2-bin model. So when we have this n here, this is actually a vector of the counts for the 2-bin model. Okay, so again, this is perhaps a lot of information, a lot of statistical jargon that's going on right here. But if we actually want to try and think about how can we use, why do we have this auxiliary data values here and what do they actually mean? We can again just try and look at what's actually in this observation area, or this input parameter here, and notice that when we look at our lookup table of the different modifiers and constraints for the HIS factory models that PyHF implements, that what we basically have here is this 1 over the background uncertainty to squared. So this background uncertainty to the -2. So if that's basically what is actually going to be our constraint information that we're using, this is what is kind of dubbed in the jargon of the HIS factory statistical model as auxiliary data. So if we look at this now, we can, since we said that this was simply just the background uncertainties to the 1 over the background uncertainty squared, then we can basically verify this by hand, because if you remember, we said that we were going to implement background uncertainties of 10 and 20% for the observed background counts. So again, since we were previously up here dealing with background uncertainties that we had put in as absolute kind of counts, and so for 10% background uncertainty for a background count of 50, then that gives us 5. So if we go ahead and actually evaluate that by hand, then when we run that just using NumPy to perform the vectorized operations, then we get values of 125. And if we go ahead and for the respective bins, and if we go ahead and actually check that using our model configuration API, then we see we get the same thing. So this has been kind of maybe a deeper dive than is necessary to go into what this auxiliary information, this auxiliary data means, but this is kind of a very simple example of just saying, okay, like how do we get from this, the information that is in this table and the information that's in our model to actually getting these numbers, because otherwise they might appear as a bit mysterious. Okay. Sorry, so I see someone raise their hand. If people have like direct questions right now, go ahead and feel free to go ahead and jump in and ask them, and we can kind of take things in stride.
Oh, yeah, thank you. Sorry, just to make, so the auxiliary data is something like an encapsulation of the relative uncertainties on the bins. Is that correct?
Well, so that is one, okay, so for this particular model, yes, because what we're saying here is that we just are, yeah. So for this particular model, we are saying that we have these uncorrelated shape systematics, but those uncorrelated shape systematics encapsulate, as you said, the information of the uncertainty on the background. Now, of course, that's just basically taking into account the statistical uncertainty of the background. But you could, of course, say like, okay, well, we live in a real world, not in just kind of this imaginary one. I have many more things that actually go into the uncertainties, both such as the systematic uncertainties that are in my model. And so this is what this kind of table gives you in the sense that this is kind of a Rosetta Stone for when we talk about these different jargony terms for the different uncertainties or modifiers, as we say, for your model, what actually goes into them and how they're calculated. But this allows you to then basically on a per sample basis go in and construct arbitrary configurations of modifiers to try and fully describe the uncertainties in your model specification.
Okay, so right, so for this very simple model, it's just statistical, and so it ends up being an array of relative uncertainties, more or less. But
exactly, yeah. So right, yeah. For this one, we're basically just trying to say like you have your counts in your histogram, and you want to also take into account, of course, the statistical uncertainty, the Poisson uncertainty. How does that uncertainty actually go into the model? And this is how.
Okay, thank you.
Yeah, no, thanks for the question. I think probably that helped clarify things. Okay, I'll try and speed up a little bit because I realize I'm already halfway through time. All right, so we have our model. That's great. We hopefully understand a little bit more about what's actually going on in this model specification. But now let's say we want to try and think about using this model, which is a full probability model for examining the actual, for examining either the predictions or the information that we can get from it. So if we first just say, okay, given this model, what is the expected data, the expected observations that I would get from this thing? If we naively just say, okay, well, there's this method here. So if I run that, okay, well, we don't get anything. We actually get a type error, and it mentions something about missing some positional arguments about parameters. And so what's going on here is that we need to say, the model doesn't by default just take guesses that without us telling it. It wants us to actually try and give it some information first about how it should actually evaluate itself for the model parameters, how it should actually try and calculate the expectation values. So now the question is, okay, what is the model parameters that we should put in? So if we do kind of the simplest thing and say, okay, like let's say we just put in 1 for all the model parameters right now. And this may or may not actually make sense, but we're just choosing 1 for the time being. How many things should I put in? What do I actually need? And if we remember, we have this, what the actual model parameters are right now. We have this scale factor model parameter for the signal. And then we also have this these gamma modifier parameters for the individual bins. But because this is a 2-bin model, there is a gamma factor, a shape systematic, or sorry, an uncorrelated shape systematic that is associated with each bin in the model. So since we have 2 bins, and in addition to this, to the scale factor, that means that we actually have 3 model parameters that are in play right now. So if we ask for the expectation values of the model for right now for a value of the signal strength and the gammas of 1, 1, 1, and we evaluate that, we actually get something out right now. But you'll notice that this might be a little bit confusing because we said, all right, well, we had 2 bins, but yet we got 4 pieces of information out. So that might seem a bit odd. And the reason why is because what the expected data returns by default is it returns both the expectation values for the actual observations as well as for these auxiliary data that we already talked about. So we can additionally, from the expected data API, also say that we want to not include the auxiliary data by passing in this can I model correlations between the auxiliary data? We should probably talk about that more because that's not going to be covered in the scope of this tutorial, but through the model, through the modifiers, you should be able to. But we should talk about that more later on, Wolfgang. Okay, so from here, we see that we can then use this just to get information about the expectation values for the observations. And if you wanted, instead of having to use this API, we also have additional APIs that kind of are more explicit about this, giving us either just the expected information about the observations or the expected information about the auxiliary data. Okay, so this all seems all right so far. So we might say, how do we actually know what these parameters are going to be corresponding to? So the way that this is actually implemented under the hood is we have these n-dimensional arrays, and because some of our backends are machine learning backends, we use the jargon tensor, which is not the mathematical tensors that we all know and love from our mathematics courses, but these are essentially, you can just think of them as n-dimensional arrays. But we do bookkeeping in a way that is maybe a little bit different with these n-dimensional arrays from just how everything is actually portrayed right out of the bat. So if we look at what actually are the model parameters, we have again listed the signal strength, mu, as well as the uncorrelated background uncertainties. And then if we also ask about what are the modifiers, then we see that we have these tuples for the model parameters that are listing the modifiers that are associated with each of them. So again, we have this normalization scale factor, this norm factor that's associated with our signal strength. And then, as we already talked about, we have these shape systematics, these uncorrelated, these shape systematics that are associated as our uncorrelated background uncertainties. However, because of the way that we do bookkeeping, the actual listing of the parameters might not always inside of the model representation in memory might not always actually be the same. And here, okay, when we evaluate them, they are, but this is not necessarily how it's always going to be. So if you want to try and get information about a specific model parameter, then you need to use the API to inquire about specific ones. Okay, so if we look again at the fact that we have 2 bins on our model, we can again query the model API to ask about this. We have a single channel that has 2 bins. And if we now want to actually look at the parameter set that is associated with our uncorrelated background uncertainties, we can get that particular object, and you can see that we have this model here. But if we want to actually ask information about how many parameters are associated with this uncorrelated background uncertainty set, we can get information about that as well. This is all information we already know, but this is a way to get it programmatically through the API. But you might not want to go through and try and like set by hand all of these all the time. You might want to just say like, okay, well, I don't want to have to go through, and if I update my model, I don't want to have to, if I just want to try and look at some default fits, or if I want to try and just get modeling very quickly, I might just want to try and take some perhaps like air quotes smart configurations and go from there. I don't want to have to manually put them in every time. So we offer that through kind of some suggested initialization parameters. So as before, if you just say from the model configuration, please generate some default starting points with the suggested initialization API, we can do that. And then likewise, all of these model parameters need to have bounds. And so they also have suggested bounds as well, whereas you can see they're kind of by default constrained between 0 and 10, which given that we're talking about multiplicative factors, that seems pretty reasonable. And then you might also say like, okay, well, I might want to have the ability to fix certain model parameters to values that I know that I want to constrain, or values that I know I want to pin. You can do that as well, but okay, thanks, Alex. Thanks, Alex, for following up on that. Sorry, so you can go ahead and just say by default, we don't actually fix any of the model parameters. We let everything float, but if you wanted to, you could pin individual ones. Okay, so we can once again replicate the same thing we did, but with this API of originally getting these initialization parameters and then asking for the expectation values of the model. And as we look at the expected data, these are the same values we saw before, 55 and 70. But now let's also say we want to try and get information about the about specific model parameters, such as the parameter of interest. And so if we ask, we have an API to do this pretty quickly. So regardless of where the parameter of interest actually lives in this list of model parameters, we can get that simply just using the POI index, because this is the one you're going to want to use the most. And in our situation, it happens to be at 0, but that's not always a given. So let's say we now want to take this initial model that we created, and we want to, with these initialization parameters, and we want to change it up a little bit, we want to say that, okay, maybe we're going to look at parameters that we think would correspond to an initialization of what a background model might look like. And in a background model, we would say that the parameter of interest might be 0. So we can do that pretty quickly by just simply getting, again, a copy of these initialization parameters, and then just using this parameter of interest index API to be able to set in that list that the initialization parameter that corresponds to the parameter of interest to 0. And now if we go ahead and run this, we see that we actually get different values because we're using different initialization parameters. Okay, so I talked a whole lot about actually setting up models and things, but what you probably want to do, since once you have this model, is you want to actually be able to try and do some statistical inference to try and say something about the physics that you're looking at. And the way that we're going to be doing this inside of PyHF is by essentially implementing maximum likelihood fits. But the way that we want to first do that is by trying to look at the different APIs that compose our kind of inference library. So the first thing that we want to say is that, okay, if we're going to actually evaluate the model to try and get information, because we're going to need to be able to do that as part of the fits, then we can look at the log PDF of that. And so we need data to actually, we need observational data. And the way that we're going to do this, given that we already showed above, that we need both observed data as well as information about the auxiliary data, we're going to simply take this list of observed data information, and this is information that we're making up here, but you can imagine that it's also, this is just simply, this is just data that we're making up, but this could be actual recorded data, as well as the auxiliary data that we're going to have, and we're going to combine this into just a single list of observations. And so note that this is actually something that's pretty common. And now we're going to simply evaluate our model for model parameters that correspond to this background only model, as well as the observations that we just recorded up here. And okay, so all we've done is we've just evaluated the model for both model parameters and observed data. And then, as you probably know from maximum likelihood estimation, you want to be working with the log of the PDF. And so that's why we have this log PDF API. And that's simply what this number is here. And we can see again that if we switch this up, so if we change the model parameters that we're actually evaluating, before we were using these background like model parameters, now we're using these initialization like parameters, that we get a different value of the log PDF. But as we said, what we probably want to be doing is maximum likelihood estimation. And so we want to try and find the maximum likelihood estimate of both of the specific model parameters, both the parameter of interest as well as the additional what are dubbed as the nuisance parameters. And so if we offer a pretty transparent API to be able to do that. So if we using the infer maximum likelihood estimate API, if we just use the fit API, we can do an unconstrained maximum likelihood fit for the observations as well as our model. And when we run that, we then get what is returned is the best fit model parameters under this unconstrained situation. And so if we just kind of read this off, then what this means is that we get a best fit model parameter, we get a best fit value for our parameter of interest of about 0.54, and then we see that we just had very small deviations away from our initialization parameters for our uncorrelated background shape systematics. Okay, so if we now want to move on to looking at simple hypothesis testing, so we've seen that we have the ability to pretty quickly do maximum likelihood fits. We might now want to try and move forward to actually do hypothesis testing so we can say things about the physics that we're actually considering. So in the interest of time, since I'm already at 40 minutes, we're going to kind of gloss over all of this, but something that you probably have all heard of before is the CLS value, which you probably have already also know is a formalism in the LHC physics community. Well, not just the LHC, the high energy physics community that allows us to create a modified pseudo-frequentist p-value for the observations, which is basically tempering the p-value of our signal plus background model by also comparing that against the background only model to make sure that we're not making statements about to help us make sure that we're not making statements where we would say that we exclude models where we basically have no sensitivity to begin with. So the important thing here is that you can basically view the CLS value as something that is p-value like, even though it's not exactly a p-value. And I think as Hans has shown in previous PyHEP talks, and I know definitely I think PyHEP 2019, this pseudo-frequentist nature has some interesting side effects, such as providing over coverage. So that's one of the reasons that it's pseudo-frequentist and not pure frequentist. Okay, but a core tenet of what we're usually trying to do is we're wanting to perform we need a test statistic to try and say something. So we want to perform a profile likelihood ratio fit. And what we're going to be doing here is basically get the test statistic that we're going to be using is actually based off of this profile likelihood ratio. And so the important thing here for just looking at this information is that the profile likelihood ratio is just saying it's a ratio of two likelihoods evaluated at different model parameters. And the important thing here is that on the bottom is the likelihood that is evaluated at the best fit model parameters for everything. The best fit unconstrained model parameters for both the nuisance parameters as well as our parameter of interest. So this is just saying if you let everything float and you perform a maximum likelihood fit, what are those best fit model parameters, and then evaluate the likelihood using them. Now, when we're doing a hypothesis test, we're saying that we want to choose a specific parameter of interest that we're actually then going to be comparing to the best fit. And so up top, up here, what this notation is indicating is that for this particular parameter of interest that we're choosing, note the little subscript on the test statistic t, this is something that we choose. And so then the double hat is saying, under the condition that we have chosen this specific parameter of interest value, what then is the best fit, excuse me, what then is the best fit model parameters for the rest of the model? And so then the ratio is then basically giving us information of for a given model, for a given parameter of interest that we choose, how close then is the evaluation of the likelihood under the best fit model parameters for the rest of the model, the rest of the nuisance parameters, to the unconstrained best fit for everything. And so this is the actual test statistic that we're going to be using to generate, to be able to calculate our p-values using the asymptotic techniques that are detailed in the paper that is linked here, that's been used for many, many years, as well as if we had time, we'll also talk about for toys. Okay, so if we're going to perform a hypothesis test, then we need to actually talk about what our hypothesis is. And there's different sorts of tests that you would do. Let's say that probably the most obvious one is to say, okay, I'm going to choose the, I'm going to say that we assume the null hypothesis of the standard model, so that if I'm looking to try and do a discovery fit, and in that situation, you would say that your signal strength for the new physics process that you're looking at is 0 as your null hypothesis, and then you'll test that against the data. But for the example that we're going to do today, we're going to do one that is maybe seen in more frequently in a lot of LHC papers, which is a limit setting or an exclusion hypothesis test. And this is operating on, this is saying, okay, if we have already done our discovery searches and we don't find anything, let's now try and set a best limit by saying, if we operate under the null hypothesis that there actually is BSM physics out there, that our signal process is perhaps for the process we care about has a signal strength of 1. How well does that agree with the data, and can we actually then try and set upper limits on where we think that this hypothesis can be excluded? Okay, so the way that we can do this is by using our inference hypothesis test API. And this allows us to get back using this return expected set keyword. This gives us back both the observed CLS value for this hypothesis, as well as the expected CLS values. And so to run through real quick what is actually being evaluated here, this hypothesis test is basically an API that allows us to configure everything that we're doing. So we're going to give it a parameter of interest that we just talked about up here. We're going to give that as a value to test. And then we're also going to give it the observations. And then we're also going to give it the model. And then we're also going to say what form of the test statistic are we interested in. And in the jargon of the asymptotics paper, we're going to be looking at the what's just called as like the test statistic, although we'll talk about alternative test statistics soon. So if we just go ahead and run this cell, we'll note that everything evaluates for this specific model parameter, and we get output, but we also get a bunch of warnings. And the reason for that is that we chose a test statistic that seems to not actually agree well with our model parameters. So just the default test statistic for a parameter of interest mu, which is known in the jargon as Q mu. So this assumes that the model parameter is unbounded at 0, so that it's able to go both above and below 0. But in the situation that we're performing an exclusions fit, so if we're doing a upper limit, we're already kind of making assumptions about what's going on here. And so for most situations at the LHC, we would say, okay, well, we have reason to believe that if we're trying to look for evidence of new physics, that we should actually be bounding this model parameter at 0, because 0 basically corresponds to our background only model. So this is PyHF then basically noticing this and saying, hey, we think you might not be using the model parameter you really want to. We're still going to go ahead and evaluate for you, but we're going to print this little warning. So now we can go ahead and actually look at this information. And as I already mentioned, if we look at our model parameter, it's actually bounded between 0 and 10, which is what we kind of want. But if we now reevaluate this using what is known in the jargon as the alternative test statistic, Q tilde, which is making the assumption that you're bounded at 0, then this runs very happily without, and it basically gives you the same, it gives you the same model, or it gives you the same observed and expected CLS values, I think almost exactly. But that's under the situation for this very simple model. Most of the time it will be true that the test statistic and the alternative test statistic will be similar, but we want to try and be very careful with how we're actually defining our model, because the model is what you actually test. Okay, and the final moments here, let's actually go ahead and do what we said we were going to do and try and set an upper limit for a BSM signal process by performing a scan and hypothesis tests. So what we want to do is we want to test many different parameter of interest, so many different signal strength hypotheses, and we then want to actually see how when we take those models and fit them to the observation, how that all works out. in the interest of time, I'm going to skip this question, but we'll get back to it as soon as we finish. Okay, so what we're going to do is we're simply just going to create using NumPy, a list of the different the list of the different parameter of interest values that we want to test that we're going to scan across. And then we're going to use the upper limit API to actually go ahead and calculate an upper limit. So this takes a few seconds, as you just saw, to run, but for a simple model like this, it evaluates very, very quickly. And we get back both an observed upper limit of a signal strength of 2.5 and an expected upper limit of 2.17. So this is great, but we might want to try and visualize this a little bit. And we can do this pretty quickly using our Brazil visualization API. And so if we go ahead and just create a figure in Access using matplotlib, and then feed this in along with our parameter of interest values and results to our API, then we get this nice Brazil band. And so here you can see that the solid black line, this is the observed CLS value for all the different parameters of interest that we tested. And then the dashed lines are indicating, well, the central dashed line is indicating the expected CLS value, and then on the deviations the dashed lines on either side are basically indicating what are the plus and minus 1 and then the plus and minus 2 standard deviations away from this for each of the POIs that are evaluated. And then you might also see down here that there is this horizontal red line. And what this is showing is this is basically a visual way for us to look at this plot and kind of read off what the exclusions are, or what the upper limit is for the different model parameters, in the sense that this line is drawn here at 0.05. And so this is the test size that we're using, which would correspond to a 1 minus itself confidence level upper limit. So if this is at 0.05, this gives us the 95% confidence level upper limit. And so we can see that the observed line, which is the solid black, crosses it just about at 2.5, and the expected crosses it at just about 2.1, which is exactly what we got up here. And so this, by basically reading where the intersection of both the observed and the expected crosses these lines, that you can basically kind of quickly read off by eye what these values should be. Okay, so I'll also just note that we make it pretty easy with this intervals upper limit API magic, but what we're doing here is not actually too complicated. So if there is, for some reason, you wanted to implement this by hand, you're able to do it pretty quickly as well, just by manually performing a hypothesis test scan across all the parameters of interest and calculating then an upper limit through interpolation. And I realized that I have just 5 minutes left, and I only got through one notebook, so my apologies there. But I'll just simply end here and invite people to both walk through the other notebooks that are in the introductory sections. And then also please go ahead and give us feedback. These tutorials are going to basically be live and updated continuously. So if you have questions or things are unclear, please just go ahead to the GitHub and open an issue and we can iterate with you there. Thanks very much for your attention. And in the final moments, I'll go ahead and take questions.
Thanks very much, Matthew. That is very normal. That you couldn't go through everything in all these 10 or so notebooks in an hour.
Yeah,
it's nice to have more material.
My apologies though for being overly rambly, because I had thought I would get through at least 3, but so my apologies there. But
no worries.
Okay, so we had a question though in one of the last ones in the chat that isn't a property of the asymptotic limit, that Q mu and Q tilde give the same p values. So off the top of my head, intuitively, I would assume that if mu hat is less than okay, so Wolfgang comments, intuitively, I would assume that if mu hat is less than 0, So if an underfluctuation observed, then Q mu and Q mu tilde should give different results. Yeah, so I think that's a good summary, Wolfgang. So I guess I would, maybe Alex, you might want to jump in here and correct me if I say something silly, but I guess I would say in the situation in which you Q, the best fit value for your parameter of interest is greater than 0, then yes, it is correct that Q mu and Q mu tilde should give you the same result. However, if as analysts we're trying to put information into our model, and we believe that given the sort of search or the sort of hypothesis test that we're performing is one in which we are saying that we expect a signal parameter greater than 0, we should want to encode that information in the model itself. And so by using the alternative test statistic, that's also saying that we are setting a lower bound on the possible values of the parameter of interest of 0. And so that's simply just encoding information. Yeah, so I don't know if that answers the question or not. And if anyone has any corrections on what I just said, but does that make sense? Or maybe because I went long, people have already bailed out, but okay, so I'll assume that given that no one else has, oh, okay, excellent. Okay, so I see that Blaze just raised their hand. Sorry, I actually don't have everything up, so maybe I should let Eduardo MC here so I don't just...
I can try to help you. Go ahead, please.
Hi, thanks very much for a very nice tutorial. I have a couple of questions from my limited experience of trying PyHF. So first of all, I'd like to know if there's any plan to have some modifiers that in practice link to samples in a fit. So I'm thinking of the case where perhaps you have two, say, signal components in a fit, and you want one or two to be floating while sort of having the other being maybe Gaussian constrained to the one left floating through a prediction coming from the theory. I wondered if, just coming through the modifiers, it doesn't appear to me that there's a very clear way to link or scale two components in a fit.
Okay, so sorry, so one more time. So you're saying that you have model parameters and you want to have some of them fixed, but then you also want to have some of them be correlated?
Yeah, so I'm just thinking of the case where I have two, say, fit components, right? And instead of having two normalization sort of modifiers, as you showed here with the mu ones, is there a way so that I can leave one freely floating and essentially relate another one through the one left floating through a scale parameter, say? Is there any way I could link the normalization of two samples in a fit?
Let's see. So I want to think for a second here before I answer, so I don't say something wrong. So yeah, so if we go back up here to the example here, then you're saying that you have multiple different samples and you're going to say that you want to have, oh yeah, okay, I see what you're saying. So you have some, let's say you have multiple different processes as samples, and you're saying that you want to try and link all of the sample, you want to link two samples together. So let's see. I want to say off the top of my head that this should in principle be possible. I would need to go and actually probably like look at the actual his factory specification. Alex might know this off the top of his head, but I believe that this is possible. We would, can you, so I'm assuming from your question that you actually have a specific model in mind when you're thinking about this. Given the time, would you mind opening a GitHub discussion on this?
Sure. I can follow up offline. And perhaps, if I may, I'd like to ask a second quick question. So regarding the, I think it's called norm sys modifier, which basically applies a Gaussian constraint on an overall normalization, say. I'm a bit confused as to what I need to supply to the modifier. Is it the actual numerical values of the 1 sigma bounds that I expect from a Gaussian constraint yields?
Okay, yeah. So here for yours, sorry, which one you said, the normalization?
The normalization uncertainty. I think it's called
Yeah.
norm cis in the actual specification, if I'm not mistaken.
Yeah. So if we go, so here I'm on the docs, and if we go to the modifiers and we look up normalization uncertainty. Okay, so.
Yeah, so in practice, my question is, the values high and low, are these just the numerical values I know the 1 sigma bands actually take for what I understand to be a way to implement a Gaussian constraint on, say, yield or normalization?
Yeah, so yeah, that is correct. So we have so what we're doing here is we're setting the sorry, just saw something in chat. Oh, okay, thank you. Alex is being awesome, and he actually just went and found a GitHub issue in which this is already being discussed. So I would recommend looking at GitHub issue 850, and we can follow up more there. Yeah, so correct. We can go ahead and since you've already looked at the documentation, thank you for doing that. And this is unclear, I'll make a note that we should go ahead and modify this to elaborate. But yeah, you're just supplying numerically what these should be.
Okay, listen, thank you.
I'm not seeing any other raised hands. Anybody? Otherwise, we're just beyond the hour.
Yeah.
So if you're interested, if it might be late for some of the attendees.
Yeah. So I'll say thank you everyone very much for your attention. Also, thank you to Eduardo and Ben and Jim, the organizers, for giving us this opportunity to talk. Please get in contact with us if you have questions. And thanks everyone for your attention. And
bye everyone. Thank you. See you next time then. Bye bye.